Welcome to Learning to Engineer. In this video, we are going to see the working of Schmidt trigger and the hysteresis concept. We will also solve some problems to get this right. Okay, so in the previous videos of this playlist, you will find out the basic equivalent circuit of operational amplifier, the necessity for DC analysis and AC analysis, and some problems associated with that. So once you watched all these videos, I highly recommend you to go to the quiz time video where there are 3 basic questions to check your understanding in this concept. So once you are done with that, you can jump to this video. Let's get started. When you are using an operational amplifier as a comparator, you will usually have a feedback at the negative terminal. So this negative feedback will provide the amplification that is necessary. When you have positive feedback, you will be able to generate a continuous stream of pulses. How? Let us see. When you have Vout at one instant and the same Vout is a constructive feedback given to the op amp, so what will that do? The error term will be added to the existing input. So let us say the output is, let us say, just 10 volt, okay, and you are giving plus 10 and minus 10 as the operational voltage. So when you get the output as 10 volt and you are adding that error to the next stream of input, so the operational amplifier will be moving to the saturation mode. Okay, so what will happen because of it? You will be getting the maximum output at the terminals of the op amp. This is how the positive feedback works. Okay, so when you don't have a feedback, when the operational amplifier works like a comparator, it compares the input at the inverting and the non-inverting terminal. When the non-inverting input is high, the output will be equal to plus VCC, the positive saturated voltage. When the input is when the inverting input is large, or when the minus input or the inverting input is large, the output will be moved to the negative saturation, which is minus EEE. Okay, so this is how operational amplifier works like a comparator. When you see a Schmidt trigger, it is a combination of both these concepts. You will have a positive feedback and it will constantly be comparing the input against the voltage at this point, which sets the level of the trigger output. Okay, so let us say you are giving a sine wave input into the negative terminal. Okay, the sinusoidal wave will be fluctuating. Okay, it will start from 0, reach positive maximum, reach 0, and again reach a negative maximum, and then back to 0. This is how a sinusoidal input will look like. Okay, so constantly when you are applying this to the negative terminal, this input at every second will be compared with the voltage at this end, at the positive end. Let us say this is called as V plus, and let's say this is called as V minus. Every instant V plus and V minus will be compared and the difference will be amplified by this amplifier. That's the concept of op amp, right? So as long as this input is lesser than the positive, the negative terminal input will be high. So whenever this negative terminal input is higher, the output will be pushed to the minus VEE, and whenever the positive V plus is high, the output will be close to plus VCC. Okay, I'll just explain this here. So when, as long as the negative terminal input is high, okay, when V minus is greater than V plus, so at this time what will happen? The output V out will be equal to minus VEE, or the negative of the operational voltage. Okay, so when the positive voltage is higher than the negative voltage, the output will be equal to plus VCC. Okay, so this is the simple concept behind this Schmidt trigger. Okay, so when the negative terminal input is 0, you will have some plus voltage here because of these two operational supplies, right? So what is the voltage across this R2? Is V plus. The voltage V plus is equal to, by voltage division rule we can calculate that it is the maximum voltage plus CCEC multiplied by R2 divided by R2 plus R3. Okay, so if you want to understand more on voltage division rule, you can check out this video and then jump back here. Okay, so the positive voltage is equal to the share of the voltage across R2. Okay, it's simple because 0 ampere is going here, R2 and R3 are in series, and in series the voltage divides. So what is the voltage across R2? It is V plus, which is this. Okay, and this is the maximum threshold point. Okay, max. Okay, and this will be equal to minus VEE, which is the negative threshold point, into R2 divided by R2 plus R3. Okay, which is LTP, and this is UTP, upper threshold point. Okay, so let's jump back to the circuit again. When the input is 0, V minus will be 0 at the starting. So it is comparing 0 versus V plus, which is this. Okay, so at this point what will happen? The V plus will be high. This is V plus, and as long as the V minus is from 0 up to this limit, the positive voltage will be higher. When V minus is equal to V plus, what happens? The output switches from plus VCC to minus VEE. Okay, so because from here up to the next threshold, up to this, the negative voltage is going to be higher, right? Only when V plus becomes higher than V minus, you will be getting the output equal to plus VCC. Otherwise, this will be equal to minus VEE. Okay, up to when you reach the lower threshold point. So at this end, this will be equal to plus VCC. Okay, so this is the concept of Schmidt trigger. Okay, when I'll repeat this. Okay, this is the input that is sent via the inverting terminal. So when the input increases from 0 volt, initially the positive voltage will be higher, V plus will be higher, right? Because you will have some meaningful amount of voltage, and this is going to be 0. This is V plus, let's say, for example. Okay, so when this increases up to V plus, the positive voltage is going to be higher. And as a result the output will be equal to the positive VCC. Okay, so output will be positive. At this instant, the negative voltage becomes higher than positive. Okay, so the Vout will be equal to minus VEE, and hence you will have a negative trigger up to the lower threshold point where this becomes equal to V plus. Okay, let us say, for example, V plus is, let us say, 2 volt. Okay, so up to 2 volt you will get a positive, and once it goes beyond 2 volt to minus 2 volt, this becomes negative. And at this point again the V minus will become more negative than V plus, and thus what will happen? You will get a positive voltage because of that, because at this region the negative voltage is even more negative than positive. So as a result V plus is higher. So you will get a positive voltage again. This is Schmidt trigger, and this is the maximum threshold and this is the minimum threshold. Okay, which is just the voltage division concept. We will solve one problem by using this concept. Okay. An ideal op-amp circuit and its input waveform are shown in the figures. The output waveform of this circuit will be dash. 4 options are given to us to choose from. Okay, so in this circuit we observe that there is an input resistor 1 kilo ohm connected to the inverting terminal, which is of no use, because if you had watched this video you will understand this concept. Okay, I highly recommend you to pause this video at this stage and then solve this problem by your own self. In this circuit, we have an input resistance of 1 kilo ohm. Since there is no negative feedback, no current flows into this circuit because there is going to be zero current going into the terminals of op amp, and if there is no feedback, there will be no current via this line. So this voltage will be directly applied over this inverting terminal. So the inverting terminal voltage is a sinusoidal voltage which is applied, and at every instant it is compared against the upper and lower threshold points of the positive supply. Let us calculate these points. The upper threshold point will be the maximum operating voltage, which is 6 volt, multiplied by 1 kilo ohm divided by 1 plus 2, 3 kilo ohm. So the upper threshold point of this circuit is plus 2 volt, meaning when the input voltage exceeds 2 volt, it will be switching to the negative operational voltage. The V out will be minus 3 volt when the input exceeds this point. Okay, please keep this in mind. Let us calculate the lower threshold. The lower threshold point of this circuit will be minus 3 volt into 1 kilo ohm by 3 kilo ohm, which is minus 1 volt. The meaning is, when the input exceeds this lower threshold point of minus 1 volt, then the output will switch to the plus VCC or plus 6 volt in this case. Okay, so let us apply these calculations to each of these 4 circuits and see which one holds good. In the first option, the input is sinusoidal. The output is sinusoidal, which doesn't happen at all. Same in the case of option B. This is not a clipping circuit. We will only have a pulsed type of waveform. So both these options are cancelled out. In the next option, at time t2, it switches from minus 3 to plus 6 or minus VCC to plus VCC. This doesn't happen because at time t2, where the input goes beyond the upper threshold point, at this instant exactly it switches from plus VCC to minus VEE. Okay, because till it reaches 2 volt, the inverting supply will be lesser. Okay, so what happens? The output will follow the plus VCC, which is 6 volt. So when this negative voltage becomes more than the positive voltage, then the output will tend to minus VEE or minus 3 volt in this case. So option D is the correct answer. Okay, so thanks for watching. For more videos on this concept, you can refer to this playlist, and you can also subscribe to my channel to get an immediate notification as soon as I publish my next video. You can also let me know your doubts, and you can also tell me which concepts to be featured in this channel. If you have any doubt, you can just share that to me at learningtoengineer@gmail.com. Thank you.